Okay, so in this video we're going to be going through the Atoms and Radioactivity exam questions that you've done. Okay, so our first question from our Atoms and Radioactivity is asking us which of these isotopes are of the same element. So remember, isotopes, they have same protons, different neutrons. So looking along our x-axis, where we have multiple atoms of the same number of protons, and we see here B, E, G. And the reason for our answer, they all have 88 protons, i.e. the same number of protons. For our radium-226, that's decaying into radon gas by emitting alpha particles. So here we need to remember what an alpha particle is made of. So we often write it like that, or sometimes with what it is, which is a helium nucleus. So remember, it has a +2 charge, and that's because it has 2 protons and 2 neutrons, giving it a mass number of 4. So we need our mass number to be the same on our left hand side and on the right hand side. So instead of this alpha particle here, I'm going to change that to 4 to alpha, because then I know that this plus 4 must equal 226. So 226 minus my 4 gives us 222, and then my 88 must be this plus 2, so 88 minus 2 gives us 86. So our answers there are 222 for the mass number and 86 for the atomic number. Okay, so our next question. A sample of radium-226 has a count rate of 400 counts per second. The half-life of radium is 1,600 years. How long will it be before the count rate has fallen to 50 counts per second? So we need to look at how many times that 400 has to halve to get to 50. That will give us the number of half-lives, which we then have to times by the 1,600. So 400 times a half is 200, 200 times a half is 100, 100 times a half is 50, so 3 half-lives, so 3 times 1600, and that's 4,800 years. Okay, in 1927, a group of women who had been employed to paint watch faces with luminous paint sued their employer over the illnesses caused by the paint. The women had been told the paint, which contained radium, was harmless. The company owners and the scientists working for the company knew that the radium was harmful and took precautions to protect themselves from the radiation. The women were given no protection. What important issue did the treatment of the women by the company owners and scientists raise? So this is an ethical issue, as they lied to them about the danger. They valued their lives more than the women who were painting the faces. So lied to them about the danger, valued their lives more than the women painting the faces. In the 1920s, many people, including doctors, thought that radium could be used as a treatment for a wide range of illnesses. Medical records that suggested radium could be harmful were generally ignored. When some of the women who had used the luminous paint died, their deaths were not blamed on radium. Suggests a reason why evidence suggesting that radium was harmful was generally ignored. So this could be for a number of reasons. So people who have invested interest in continued use of radium could cause public unrest. Doctors don't want to be blamed for illnesses where they were previously recommending radium, and the doctors might have thought that the benefits of its use outweighed the risks, so they could have believed that that treating using radium outweighed the risk of the illness. So any one of those, I'm just going to put down that they didn't want to be blamed for illnesses. But anything along those kinds of lines. Okay, so question 2, describe the structure of an alpha particles. So I have this in question 1, but it's a helium nucleus consisting of 2 protons and 2 neutrons. What are beta particles? So these are high energy electrons. High energy, so they're fast moving. How beta radiation is produced by a radioactive isotope, and this is where a neutron becomes a proton and an electron. Question 3. 2 of these atoms are from the same element. Which of A, B and C is of a different element? So we need to be looking at our numbers of protons. So same element will be same number of protons. So we know it's B as they're atoms, so our number of protons and electrons must be the same. So 3 here, 3 here, 4 here. So where we've got 3 and 3, they are the same, whereas B has 4, so it's different. So reason for the answer, B has 4 protons, whereas A and C have 3 protons. Two of these atoms are isotopes of the same element, so therefore that must be A and C, and this is because they have the same number of protons, where we've got 3 and 3 shown by the blacks, and then the whites must be shown on neutrons, 3 and 4, different number of neutrons. And so they've got a different mass. Which of the particles has a positive charge? So this is our protons, so that's our circle, our black circle, sorry. No charge is our neutron, and our smallest mass is our electron. Using the same symbols as those in the diagrams, draw an alpha particle. So we're wanting 2 protons and 2 neutrons. Okay, so question 4 is looking at our models of our structures of atoms. So we've got the plum pudding model, where you've got the positive sponge with the fruit electrons scattered through it. And then we've got the nuclear model, which is Rutherford's model, where you've got the electrons now orbiting a positive nucleus. So describe the differences between the two models of the atoms. So our nuclear model has a nucleus where the mass is concentrated, whereas in the plum pudding model the mass is evenly distributed. We can also say that in our nuclear model, the majority of the atom is empty space, whereas the plum pudding model shows the atom to be a solid mass, so no empty space. You also could have talked about the electrons being orbiting the nucleus in the nuclear model, whereas in the plum pudding model they're embedded in the mass. You could have talked about the positive charge being concentrated in the centre of the atom at the nucleus, whereas in the plum pudding model, similarly with the mass, it's evenly distributed throughout the model. So into question B now. In their investigation, Rutherford and Marsden fired positively charged alpha particles at a very thin sheet of gold. Over a period of several months, the scientists made over 100,000 measurements. These measurements showed that a very small number of alpha particles were deflected backwards from the gold foil. We used the nuclear model to explain this experimental result. So the fact that the alpha particle is being deflected shows that it's being repelled by something. So if it's being repelled, it must be something of the same charge, and so this showed that the nucleus was positive. So the deflection of alpha particles showed that the nucleus was positively charged, and it also showed us that our nucleus is very small, as few of those particles were deflected. So as only a small number were deflected, the nucleus is small as the rest must be empty space for the particles to pass through. Why did the work of Rutherford and Marsden convince many scientists that the plum pudding model of the atom was incorrect? So they took over 100,000 measurements, and so they were the data that they got from that was taken to be reliable, and their findings could not be explained by the plum pudding model that was already in existence, and so that led them to think that that model was therefore wrong. So the many measurements that were taken gave reliable data that could not be explained by the plum pudding model. Okay, question 5. Carbon has 3 naturally occurring isotopes. The isotope carbon-14 is radioactive. An atom of carbon-14 decays by emitting an alpha particle. Complete the following sentences. The atoms of the 3 carbon isotopes are the same as each other because they have the same number of protons. And they are different because they have different numbers of neutrons. What is a beta particle and from what part of an atom is it emitted? So it's a high energy electron. From the nucleus of the atom. So you might be tempted to say high energy electron from the shells of an atom because that's where you find electrons. However, remember that actually this beta particle has come about because a neutron has changed into a proton and an electron, and so that electron has come from the nucleus because it's come from where that neutron was. Okay, so carbon-14 is constantly being made in the atmosphere, yet for most of the last million years the amount of carbon-14 in the atmosphere has not changed. So how is this possible? So that means that the rate at which it's made must be the same at which it's decaying, because remember carbon-14 is radioactive, so it's going to be decaying randomly, but that rate of decaying must be the same as the rate at which it is made for there overall to be no change. So your rate of decay, same as the rate at which it is made. Trees taking carbon-12 and carbon-14 from the atmosphere. After a tree dies, the proportion of carbon-14 in the tree decreases. Graph A shows decay curve for carbon-14. So Lake in Ecuador was formed after a volcanic eruption. Carbon taken from a tree killed by the eruption was found to have 10.5 counts per minute. At the time of the eruption, the count rate would have been 16 counts per minute. Use graph A to find the age of the lake. So we want to go to where 10.5 is on our graph. So 10.5 is therefore here. And we want to read down to here. So 5,000 is our 10 squares, and we've got 1, 2, 3, 4, 5, 6, 7 of those small squares, If 5,000 squares is 10 squares, then 1 square is 500, so 7 times 500 is our 3,500 years. Okay, finding the age of organic matter by measuring the proportion of carbon-14 that it contains is called carbon dating. This technique relies on the ratio of carbon-14 to carbon-12 in the atmosphere remaining constant. However, this ratio is not constant, so the age found by carbon dating needs to be adjusted. Use graph B to adjust the age of an object found by carbon dating. The value obtained from graph B will be no more than 50 years different to the true age of the graph. Use graph B and the information above to find the maximum age that the lake could be. So using the graph, we want to go to where that 3,500 is. So 3,000 is here, halfway between, be about there. So that comes out as 3,000, 3,200, 3,400, 3,600, 700. So 3,700 is the adjusted age. However, no more than 50 years different to the true age. So the maximum it could be is therefore 3,700 plus 50, so 3,750 years. Okay, so here we're looking at a system used to control the thickness of aluminium foil as it is being rolled. A radiation source and detector are used to monitor the thickness of the foil. Which type of source, alpha, beta or gamma, could be used in this control system? So this all comes down to how penetrating our different sources, our alpha, beta, gamma are. Our alpha, if we remember, is stopped by paper. Beta, 3 mils of aluminium. And our gamma needs thick lead and concrete. And so paper, any thickness of the aluminium is going to stop the alpha. Beta, however, some will pass through if it's too thin, but if it's too thick, it would be blocked. Our gamma, all of it would pass through any thickness of the aluminium, so it has to be beta. And now explaining why our other two would not be suitable. So alpha would be blocked by any thickness, and so passes through, and our gamma would not be blocked by changes in thickness, and so would always pass through, and there'd be no change in the count rate. So here's a chart showing how the count rate recorded by the detector varies over a short period of time. So here we've got a dip in the count rate, and then it goes up to a peak and then back down to the equilibrium. So this equilibrium will be the ideal thickness, whereas where our count rate decreases, it's too thick, and here it's going to be too thin as more gets through. So So explaining how the thickness of the foil changes and how the control system responds to the change. So where our foil thickness increases, the count rate decreases, and so the pressure of the rollers increases, the thickness then decreases, and the count rate increases, pressure of the rollers decreases, and then returns to the normal thickness and pressure. So foil thickness has increased, count rates increased, so then the pressure increases, which causes our foil thickness to decrease and therefore our count rates to increase, and therefore our pressure can be reduced and it will then return to a normal thickness and normal pressure. Part C. When first used, the radiation source contains 6 micrograms of strontium-90. The graph shows the mass of the strontium-90 will decrease as nuclei decay. The control system will continue to work with the same source until 75% of the original strontium-90 have decayed. After how many years will the source need replacing? Show clearly your calculation and how you use the graph to obtain your answer. So if 6 is the 100%, then 3 is going to be when 50% has decayed, and 1.5 when 75% has decayed. So you need to go to where 1.5 is on the graph. So 1, 2, halfway here, and it looks to cross here. So measuring that down, so 52 for 56 years. So you're showing clearly your calculation here. 75% of 6 is 1.5. So then using graph, 1.5 micrograms gives us 56 years. Okay, we're back to looking at our plum pudding model. So those scientists knew atoms contained electrons and the electrons had a negative charge. They also knew the atom was electronically neutral overall. What did this allow the scientists to deduce about the pudding part of the atom? Well, if the electrons are negative and overall there is no charge, our pudding must be positive. And that it's an equal amount of positive compared to the negative. Okay, if the plum pudding model was correct, then most of the alpha particles would go straight through the gold foil. A few would be deflected, but by less than 4 degrees. The result of the experiment were unexpected. Although most of the alpha particles did go straight through the gold foil, about 1 in every 8,000 was deflected by more than 90 degrees. Why did this experiment lead to a new model of the atom called the nuclear model, replacing the plum pudding model? So our experiment results here could not be explained using our plum pudding model, and so they didn't support this model. Experimental results could not be explained by the plum pudding and so this diagram shows the paths A, B and C of 3 alpha particles. The total number of alpha particles deflected through each angle is also given. Using the nuclear model of the atom, explain the 3 paths A, B and C. So a nuclear model is our one with nucleus in the centre and our orbiting electrons. So A, 0% deflection, and we had 130,000 alpha particles. So this showed that most of the atom is empty space. For those particles to be allowed through. So this is talking about the part where the electrons are orbiting, as this is mostly empty space, but you will have an electron orbiting around, but at any one time particles can pass through as it's mainly empty space. So our B, we had a 30-degree deflection with 80,000 alpha particles. So this is showing us some repulsion, which shows us that the nucleus is positive. And here, 150-degree deflection, 30 alpha particles. This shows us that the nucleus is very small. And that's because of the small number of particles that weren't able to pass through. Shows us how small that mass must be for them to have that backwards rebound compared to just a deflection as they're passing by the nucleus. So C is as a result of being in line with the nucleus and therefore being deflected. So the low number of particles is what tells us that. Part II. So using the nuclear model, E. Rutherford devised an equation to predict the proportion of alpha particles that would be deflected through various angles. The results of the experiment were the same as the predictions made by Rutherford. What was the importance of the experimental results and the predictions being the same? So this is that it supports the new model. So if his prediction is right and the experiment results are right, then they're supporting one another. Okay, there are many different isotopes of gold. The isotope gold-198 is radioactive. An atom of gold-198 decays by emitting a beta particle. All atoms of gold have the same number of protons. As remember, it's the number of protons which defines our atom. And the same number of electrons for them to be an atom. The atoms from different isotopes of gold have different numbers of neutrons, which gives them a different mass number for the different isotopes. A beta particle is an electron, originated from the nucleus of an atom. Remember, the electron is formed from a neutron changing into a proton and electron, so it's come from the nucleus where that neutron was. Use the graph to calculate the half-life of gold 198. So our half-life is the time taken for half the sample to decay, or time for the activity to halve. Both happen at the same time, because if you're halving the amount there's going to be less decaying, and so therefore your activity would also have halved. But it just depends on what your y-axis is as to which definition we're working with. So here we're looking at a count rate, and so we're looking at our activity. So if it's starting at 600, our half-life is going to be the time it takes for it to get to 300, which is here. And that looks 2.7 days. So here they've asked you to show on the graph. So I would, using a ruler, make sure you're drawing your lines down and along, showing that clear half from 600 to 0, but you could have picked any other point and halved it. So for example, 500 is here, and then you want to go to where 250 is, which is here, and that distance should be the same, as the half-life is constant. So our distance from here to here should be the same as the distance from there to there. If you took 400 here to 200, which is here, again that distance should still be the 2.7 days. Doesn't matter where you start, so long as you're halving your activity and reading off the points of the graph and then looking at the difference between them. I always find it easiest choosing my first one as the 0, because it then just means I can just read off my x-axis as to what the half-life is, but you could choose any of these points, halve it, so long as you've still got a corresponding point on the graph to match it up to. So the diagram shows a map of a river and a river estuary. Environmental scientists have found water flowing into one part of the river estuary is polluted. To find where the pollution is coming from, the scientists use a radioactive isotope of gold 198. The gold 198 is used to find where the pollution is coming from. Explain how. So by putting the source into water at a certain point of the bank, they can see if the radiation is detected in polluted areas. They could then test different parts of the riverbank at different times to see whether there's any difference, and whether it's detected downstream of the factory or the farmland or the sewage treatment, to then identify the cause of the pollution. So the source is put into water at one point on the bank, and then see if radiation is detected in polluted area, and that will tell us where the pollution is coming from by then testing at different parts to find what the source of the pollution is. So that was our final question for atoms and radioactivity, so thank you for watching.